Good morning, everybody. Give people a couple minutes to join us this morning. Actually, let's see if I have something fun to do. All right, give everybody about 1 more minute to join. Then we will start on chapter 20. We got 1, 2, 3, 4, 5, 6, 7. Good morning. All right. Well, why don't we jump right into it? Let me share this screen, lecture notes. Okay, so we are going to cover chapter 20 today, and it's a relatively short chapter. I'm going to cover the entire thing today. So I touched on it a little bit on my last lecture, so let me just do a quick little review of what I've covered so far. So all sound, every sound that you could possibly imagine is all produced by the same thing, and that's some object which is oscillating back and forth. For example, if I'm talking about, music, all music is basically created by some object which is oscillating back and forth. If we're talking about, oops, must have turned off. Hold on 1 second. Okay, so if we're talking, whoa, that happened. If we're talking about a guitar, whoops, I just got a new tablet. If we're talking about a guitar, right, what's oscillating back and forth in the guitar is just the string. And I'll talk about this a little bit later, but the whole purpose of the sounding box, so all guitars and things like that have basically this wooden structure around it. What ends up happening is the guitar string vibrates back and forth. That causes the air in the guitar to start to oscillate back and forth. And the more air that oscillates back and forth, the louder the sound's going to be. Any kind of wind instrument, like a flute, you basically have the air inside the instrument oscillating back and forth. If we're talking about your voice, it's basically your vocal cords oscillating back and forth. What ends up happening is that oscillating object will basically send a disturbance through the medium. We generally think of sound traveling through air, but it doesn't have to be air. It's usually air, but sound can travel through any elastic substance, something that can oscillate back and forth and restore its shape. So let me stop this for a second and then just show you a little example of what I'm talking about. Where's my PowerPoint slides? So let's share those. Okay, so sound is a longitudinal wave, and that's one in which the way the medium is disturbed is along the same direction as the way the wave is traveling. Classic example is moving a slinky back and forth. So in this case, the slinky is being disturbed horizontally back and forth, and that's also the direction that the wave is traveling. So in this case, we would call that a longitudinal wave. So this is pretty much how all waves are produced, is something is oscillating back and forth. If we're talking about our voice, that might be your vocal cords. If we're talking about a guitar, it might be the guitar string. Something moving back and forth at a certain frequency produces a longitudinal wave in air or whatever the medium is. So this oscillating object moving back and forth causes the air around it to start to oscillate back and forth. And when the air gets closer together, I have a region of higher pressure. Where the air is farther apart, I have a region of lower pressure. That pressure wave of the air oscillating back and forth It's what's actually traveling through the air or through the water or something like that. One cool thing is, if you look at this animation, it kind of looks like I have a bunch of air which is traveling from one direction to the other. But if you focus on any one dot, and this could just be an air molecule, which you'll see if I can highlight one of these. If you kind of look, let's say over here at one dot, this dot is just oscillating back and forth. It's not actually moving from one side to the other. It just oscillates back and forth. And the frequency that it oscillates back and forth at will be the same as the frequency of whatever's producing the sound. So for example, I wish I had brought some tuning forks, but tuning forks are meant to always oscillate back and forth at the exact same frequency whenever you hit them. So whenever the tines, the little ends of the tuning fork, move farther apart, it compresses the air. I get a region of high pressure. And when they move closer together, I get this region of lower pressure. And it's that pressure wave which is actually traveling outwards. And then I'll show you in a second, what ends up happening is once that gets to your eardrum is basically just this little part of your ear that can oscillate back and forth. And if this is the whoa, I don't know what happened there, hold on. If this is the inside of your head, the pressure here is at atmospheric pressure. But the pressure out here is changing. Remember, anytime there's a difference in pressure, I end up having a force pushing from higher pressure to lower pressure. So if the pressure outside your head changes, that's going to cause your eardrum to start to oscillate back and forth. And the frequency your eardrum oscillates back and forth at is going to be the same as the frequency of the sound wave. So a speaker, anything that produces sound from a stereo or something like that, inside every speaker is basically just a diaphragm, which is usually just a piece of paper, something like that, which oscillates back and forth. And again, when the speaker is moving outwards, I get the air getting compressed together. When it's moving back, I get the air being farther apart. And it's this pressure wave, which is actually traveling through the air. Let's not worry about that. But once it hits your ear, if there's a difference in pressure on one side of your eardrum than the other, there's going to be a force pushing your eardrum towards the higher pressure region. So this might be a speaker, which is oscillating back and forth, which causes these air molecules to oscillate back and forth. And this pressure wave then gets to your ear. And what it ends up happening is, so again, it's funny, I spent way too long trying to get this animation set up. I've got something which is oscillating back and forth at a certain frequency. That causes the air molecules around it to oscillate back and forth at that exact same frequency. That then travels outward, gets to your eardrum. And then what ends up happening is the pressure right here on the inside of your head doesn't change. That's basically atmospheric pressure. But then the pressure outside your ear is going to change, and that's going to cause your eardrum to oscillate back and forth. Now inside, I think it, inside the little part of you. Oh wait, I think I figured something out. I can turn off gestures. Okay, so inside this little part of your ear, you've got all these little hairs. And what ends up happening is when your eardrum oscillates back and forth, it causes these little hairs in your ear to oscillate back and forth at the same frequency that then sends a signal to your brain, and your brain sort of interprets that as sound. So that's just a little introduction. Let me pause for a second. Are there any questions I can answer just about how sound is produced? So all sound, some object which oscillates back and forth, sends this pressure wave through the air, these air molecules oscillating back and forth, then hits your eardrum, causes your eardrum to oscillate back and forth at the same frequency, and then that signal gets sent to your brain, and then your brain does whatever it does. So let me just stop for 30 seconds. Are there any questions that I can answer just about how sound is produced and how we hear it? Going once, going twice. Sold for no dollars. Okay, let's continue. So one important thing to keep in mind about sound is that all sound is produced by something which is oscillating back and forth, and the frequency of the object is going to be same as the frequency that the object that produces the sound is oscillating at. So for example, if I had a, well, I wish I had a speaker that I could vary, but a 100 hertz sound is produced by something which is oscillating back and forth 100 times every second. A 1000 hertz sound is produced by something which is oscillating back and forth 1000 times a second. And what we call pitch is basically our interpretation of frequency. We hear high-pitched sounds produced by objects which are oscillating back and forth at high frequency. So high frequency, my vocal cords are oscillating back and forth very rapidly. A low frequency sound, a low pitch, means they're not oscillating back and forth very rapidly. Now, the human, one more time, the human ear can hear frequencies from about 20 hertz to 20,000 hertz. And this, however, is for a normal young adult. What ends up happening is as you get older, this frequency range drops. So the older you are, this high frequency drops. So for example, for me, so if we were in class, I would have done a sound test where I would have had a speaker. I would have just started playing frequencies out of it and then just start cranking it up. I can't hear above about 15,000 hertz. So what you would see is that I'd start cranking up the speaker. Once I got to like 17, 18,000 hertz, only the youngest people in the class can hear it. So it ends up that there are sounds that are out there that you cannot hear. For example, a dog whistle. I don't even know if they have these anymore, but a dog whistle was just a whistle that would produce a sound over 20,000 hertz that only dogs could hear. Humans can't hear that high. Couple interesting things. So only normal teenagers can hear high frequencies of around 20,000 hertz. So a couple interesting things. One, I don't know if they still have this, but they used to have what's called, let me just stop this for a second. So they used to have what's called, and let me do speaker view, see if that changes the way it records this. Hey, I like this. I'm in the Millennium Falcon. I don't know if they still have this, but they used to have something called the mosquito ringtone. And that was basically a ringtone that was up at like 17, 18, 19,000 hertz that only younger students could hear. And so the whole theory was you could have your cell phone ring during class and teachers wouldn't be able to hear it because we can't hear high frequencies. Other interesting thing is in some countries, I think it's in England, to prevent people from loitering around, let's say the 7-Eleven equivalent there. They would have these speakers that would just play a really high frequency sound of around 18, 19,000 hertz. It would drive young teenagers hanging out near the 7-Eleven crazy because it's just a really high frequency, annoying sound, but older adults couldn't hear it. Brian, question.
Yeah, I was just, are we continuing chapter 20? I'm sorry, because I joined like a minute or two late and you didn't have your recap on, so I was just.
Yeah, so actually I didn't put the recap on. I'm just sort of continuing chapter 20. I'm going to finish it today. And
Okay.
Yeah, we'll be all done.
Okay,
Suki,
that was my only question.
Okay, Suki, do you have a question?
No.
Oh, okay. All right, any questions I can answer about that? So real quick, why do older adults why are we not able to hear these high frequency sounds? Well, keep in mind that
old?
I was looking for a more scientific explanation. So in order to hear a 20,000 hertz sound, those little hairs in your ear that oscillate back and forth at the same frequency that your eardrum does, they have to be able to oscillate 20,000 times a second. So what I think happens is that as you get older, these little hairs in your ear get more brittle and they cannot oscillate back and forth as quickly as they could before. So if they can't oscillate back and forth 20,000 times a second, you're not going to be able to hear that sound. So as you get older, those little hairs start to become more brittle. Some of them can even sort of, I think, die and stop working, but they can't oscillate back and forth as quickly. Okay, let's keep going then. Let's go to PowerPoint. No, sorry, I don't want to do that. I wanted to share OneNote. Okay, couple things let me just say about this loudest sound. So just actually, let me go back to this new share again, PowerPoint slide. So this eardrum moving back and forth, how much it's moving back and forth in this animation is greatly exaggerated. Your eardrum hardly moves at all. So just to give you an example, so the loudest sound that you could hear, or basically if I just started cranking up the volume of some sound, at some point it would be painful and unbearable. The loudest sound that you can hear, your eardrum is only moving back and forth about 10 to the minus 5 meters. So about 1/7 the thickness of a sheet of paper. That's how much your eardrum is moving back and forth when there's a sound that's almost as loud as you could bear. Now, if I was just whispering and barely talking at all, the faintest sound that we can hear, our eardrum is moving back and forth about 10 to the minus 11 meters. That's 0.0000000000001 meter, about 1/10 the radius of an atom. So our eardrum is unbelievably sensitive. And just as a quick aside, I've taken many martial arts in my life. If you've ever seen a movie where somebody grabs somebody and then they clap them in the ears and they're all like, ah! It's actually an unbelievably effective self-defense technique, because if I could send this really fast pulse of air into your ears, the eardrum is so sensitive that a fast enough pulse of air could actually shatter your eardrum. And then once your eardrum shatters, you're never really going to be able to hear it the same way again. So anyway, that's a little aside. All right, so going back, lecture notes. A couple of things I want to emphasize is that one, sound does not only travel through air. Air is pretty much where we always hear sound through, but sound is not only transmitted through air. In fact, it can be transmitted through any sort of elastic substance. And that's just a substance that, like, when I push it, it'll tend to sort of push back. So like if I threw a piece of silly putty against the wall, it would just sort of mush against the wall. That's not really something that's going to oscillate back and forth and produce sound. But it ends up that sound will actually travel faster in a solid than it does in a liquid, than it does in an air. So you don't need to know these exact numbers, but just to give you some ideas, sound travels 4 times faster in water than it does in air, and about 15 times faster in steel than it does in air. So one of your questions, I think, for the homework is, why is it that like a Native American or somebody might put their ear, why would somebody put their ear on a train track in order to hear it, or blah, blah, blah. Actually, let's see, do I have a homework question for that one? No, so I didn't ask that as a homework question, but why do, if you were to watch like an old Cowboys and Indians movie, sometimes you'll hear people put their ear to the ground. The reason they might do that is because sound travels faster in a solid object than it does in a liquid, than it does in the air. So for example, 15 times faster in steel. So if you were on, let's say, a train tracks and you wanted to have advanced information about whether or not the train is coming, if you put your ears to the track, you'll hear the vibrations through the steel 15 times faster than the vibrations through the air. So whenever you heard, let's say, like a Native American in the movie putting their ear to the ground, what they were trying to do is hear the sound through the solid ground, because it would be faster than hearing the sound through the air. So in general, sound travels fastest in a solid and slowest in a gas. And one thing, sound cannot travel in a vacuum. And the reason is, if there's nothing to compress or expand, you can't have any sound. So if I had a tuning fork, as the tuning fork moves back and forth, it sends a disturbance through the air that eventually reaches your ear. But if there is no air around the tuning fork, then these things just moving back and forth, but there's nothing to compress and expand, so you're not having any sound generated. So I wish I could show you this demo on Cabrillo, but what I want to do is show you a video. And this is a video of there's basically a speaker or something inside a vacuum chamber. And we're going to do is pump out the air. And you'll hear that once the air is pumped out of the jar, you cannot hear any sound coming from the jar.
So the air can't get in, and open this valve to allow our vacuum pump to suck out the air. The air is being sucked out now, and you should see the sound level dropping on the microphone. So
just real quick, we're not going into decibels, but we measure how loud sound is using a scale called decibels. And this is just showing you that the level of the sound is dropping dramatically. And
you can see our gauge reads 0. And also the levels in the microphone have completely dropped. That's because a sound source vibrates and that pushes the air and transfers the vibration to you hearing it. But because there's no air in our vacuum, the alarm is vibrating, but it can't transfer that to the microphone. So I'm going to do the reverse now. I'm going to shut this valve and then open this valve. So the air's back in now, and the microphone's picking up the sound, and I can just about hear it as well. So that's been our experiment.
Okay, so it's not less exciting watching it on a video, but what I would have showed you in class, same thing, would have put a bell in a jar, played the bell, and then pumped out the air, and you'd hear as the air is getting pumped out, you start to hear less and less of the bell, and then eventually you can't hear the bell at all. So one cool thing, well, not really cool thing, but one of your questions, one of your homework questions is what 2 mistakes occur in a science fiction film where you hear and see an explosion at the same time? So 1, there is no sound in space. And I mentioned this, if you saw the original Alien way back when, the tagline for the original Alien was, "In space, no one can hear you scream," which is exactly right. So if you were in space, you're like, ah! Your vocal cords are oscillating back and forth, but there's no air around it to transmit that sound. So in a sense, there's really one mistake. 1, you would never hear an explosion in space. So any of those science fiction movies where you hear this tremendous explosion happening, not gonna happen. 2, sound travels about 1,000,000 times slower than light. Or put it the other way, light travels about 1,000,000 times faster than sound. 1, that's why we always see lightning before we hear thunder. And just as a rule of thumb, just so you know, sound travels it takes a sound about 5 seconds to travel 1 mile. The speed of light is so fast that light pretty much travels about instantaneously. So if you see lightning and then start counting, every 5 seconds between when you see the lightning and when you hear the thunder, that lightning was about 1 mile away. So you see lightning, you start counting, you get up to 5, and then you hear the thunder. That means that particular lightning strike was 1 mile away because it takes sound about 5 seconds to travel 1 mile. Also, if you've ever been to a baseball game where you're sitting sort of in nosebleed seats, it's kind of interesting. Even just a baseball stadium, the distances are big enough that you will hear the crack of a bat hitting a ball after you see it, just because it takes sound some time to travel. I totally forgot what I was talking about. Where was I going with this? Oh yeah, so in space, there is no sound. And so 2 mistakes that in a science fiction movie where you see and hear an explosion at the same time, 1, there's no sound at all. But 2, even if there was sound, you would see the explosion, and then much, 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 much later, the sound would finally get to us. Okay, so going back, not to that. discard. Let's go back to sharing screen. Okay, so a couple things about sound. Remember, for all waves, this wave speed does not depend upon the frequency or the wavelength. It depends upon properties of the medium. So for sound, how fast sound travels in a material depends upon certain characteristics. And if we're talking about sound in air, it depends upon three things. We're only going to focus on one. One, it depends upon the wind conditions. Sound will travel at a different speed on a windy day than on a day where there is no wind. It depends upon humidity a bit. If it's very humid out, that will change the speed at which sound travels. But the one I want to focus on just a little bit is temperature. Speed of sound in air depends upon the temperature. And it's kind of the opposite of what people think from my experience. So we know in a wire, as the wire heats up, the resistance of the wire increases, which makes it harder for current to flow through it. But sound is kind of the opposite. Keep in mind that in air, you've got these molecules which are moving around. As the air heats up, whenever things heat up, the air molecules and everything start moving faster and faster and faster. Well, the way sound is basically transmitted is these air molecules oscillating back and forth, running into other air molecules, and then passing that sound pulse. Well, if the air is already moving faster because it's hotter out, then you're going to be able to transmit a sound pulse in less time. So it ends up that the greater the temperature, the greater the speed of sound. And the reason is just because the air molecules are already moving faster, which means they're going to be able to transmit a sound pulse in less time. Okay, so like I was saying, faster moving molecules in warm air, they bump into each other more often and therefore can transmit a pulse in less time. And you don't need to know these exact values, but the speed of sound in dry air at about 0 degrees Celsius is 330 meters per second, or about 750 miles an hour. So in most everyday situations, you can imagine sound traveling at about 750 miles an hour. Okay, let's pause for a clicker question or two. And I've been trying to do these polls. They don't seem to be working great. So I'm just going to ask this as a question for you to think about for a second. First one, 20.1. Speed of sound. The speed of a sound wave in air depends upon A, its frequency, B, its wavelength, C, the temperature, D, all of these, E, none of these. What do you think? The answer is not A. The answer is not B.
The temperature.
Answer is the temperature.
That's exactly what I was thinking.
Yeah. And as a little follow-up, and again, there's a good chance you're going to see a question like this again sometime in the future.
This question or the past question?
Well, some variance of, let's say, if I change the frequency of a wave, how does that affect the wave speed? Something that's just emphasizing the fact that the speed of sound, the speed of any wave, doesn't depend upon the wavelength and the frequency, depends upon the properties of the medium. So going back, thinking about this one then, 22. If the frequency of a sound is doubled, what change will occur in its speed and in its wavelength? So again, wave speed for any wave only depends upon the properties of the medium the wave is traveling through. So in this case, the wave speed is not going to change, so it's going to be the same. But keep in mind, if the frequency of a wave goes up, the wavelength goes down, or if the frequency were to go down, the wavelength would go up, but the speed is the same in both cases. So the wave speed stays the same. If I double the frequency, then the wavelength is going to be cut in half. So the correct answer would be D, cut in half. So again, keep in mind, if higher frequency sounds traveled at different speeds, we would never really ever be able to have music the way we do. because music is just a combination of, you know, many, many, many different frequencies, but these are all arriving at our ear at the same time. If the different frequencies of sound travel at different speeds, then you're going to hear high frequency sounds at a different time than low frequency sounds. They're all going to arrive at a different time. Music would be virtually impossible. Actually, I was starting to think about this. If the speed of sound did depend upon frequency, then what you would have to do is set up a concert where the sounds that traveled faster, you'd have to put those instruments farther away than the sounds from instruments that traveled slower, and you'd have to have all of these musicians lined up at different distances away from you, and it would be chaos. All right, let me pause this for 1 second. Let me just open it up. Are there any chats? What I mean, any questions on anything that I've covered so far about sound?
I have a question.
Okay.
So if a tree fell in the forest, but nobody was there to hear it, would it still make a sound?
It would, well, the answer is, it depends on how you define a sound. I would answer that question as yes. So once a tree falls, it's going to cause the air around it to oscillate. So the question really is, do you consider it a sound if nobody is there to hear it? I would answer yes. It's still producing oscillations in the air. And just because there's nobody there to hear it, doesn't mean there's no sound. It's almost like if I play music from a jukebox in a forest and nobody's there to hear it, does it still make a sound? The answer is yes. It's still producing oscillations within the air. It's just there's nobody with an ear there to hear it. Other questions? All right, what do we got? About 20-ish minutes. All right. We only have a few more things to cover on this chapter. So going back to lecture notes. Okay, so just as I was saying before, all sound travels at the same speed regardless of the frequency of the sound, how loud the sound is, or the wavelength of the sound. Okay, let's do a new share. Let's go back to this PowerPoint. Okay, a couple questions for you. Let's not worry about that one. So one, why is the moon described as a silent planet? And the reason is there is no atmosphere on the moon. If there's no atmosphere, there's no air, there's nothing to transmit sound. So the moon is described as a silent planet because no atmosphere. Now, I think I mentioned this at one point when we were talking about gravity in the Earth's atmosphere. Most scientists now believe that the Earth once had an atmosphere, but most scientists believe that the moon once had an atmosphere. The moon's gravity is so much weaker than the Earth's gravity that those atmospheric molecules eventually just dissipated out into space, and now there's no atmosphere around the moon. Okay, let's talk a little about reflection. Remember when we were talking about standing waves, when a wave hits a boundary, so I've got some wave coming in, when that wave hits a boundary, there's a few different things that can happen. One, that wave can get reflected back. Two, that wave could get absorbed. And then three, that wave, some of it could get transmitted through. We'll talk about that with terms of light. But thinking about sound, when sound hits a surface, some of that sound is going to get bounced back. We call that reflection. Some of that sound can actually get absorbed. And so what is an echo? An echo is really just a sound wave which is hitting a rigid object, and some of that sound is getting reflected. So an echo is really just sound that gets reflected off of a surface, and not all sound is going to get reflected. Pretty much anytime it hits a surface, some of that sound is going to get absorbed. How much gets absorbed, how much gets reflected, really depends upon a couple things. One, it depends upon how rigid the surface is and how smooth the surface is. So in general, a rigid, smooth surface will reflect sound really well. A soft, porous surface will absorb sound really well. So as a little hint, one of your questions for the homework says, why is it so quiet after a snowfall? And the answer has nothing to do with the speed of sound. When it's cold out, sound travels slower, but how loud the sound is doesn't depend upon how fast the sound is traveling. Why is it so quiet after a snowfall? It's because snow is very soft, very porous. It's a very good absorber of sound. Much of the sounds that we hear outside are being reflected off of objects that then hit our ear. So if I cover the entire surface of the ground with something that absorbs sound really well, then I'm not going to hear any reflected sound off the surface. And so it's so quiet after a snowfall, simply because sound is a really, really, really good absorber of snow. Snow is a really, really, really good absorber of sound. And this is also why, if you go to the movie theaters, you guys remember those? A couple months ago, we used to be able to go out and go to movies. At the sides of movie theaters, there's always these curtains there. And the reason is curtains are sort of very soft and porous. The curtains will absorb the sound so that I don't have as much sound traveling from one theater to the next. Okay, so also, there's a whole branch of physics just called acoustics that really look at how theaters and how concert halls are going to be designed, because you can have sound waves interfering and producing interference, which can mess up the way the sound is. So one cool thing, I don't know how well you can see it, but some really nice concert halls, what they have is they have these very smooth, highly reflective things up here. And what they're basically doing is, these musicians are creating sound, but the sound doesn't travel in a straight line. It sort of travels out as a sphere. So a lot of the sound is, coming straight out towards the audience, but some of it is also moving upwards. And so these things are designed to reflect the sound back towards the audience. And so really nice concert halls spend a lot of time looking at how the speakers are set up, how the surfaces are, so that you get the optimal experience. Quick little story. I'll just stop this for 1 second. I went to the very first concert they had at the new stadium, the new Giant Stadium. Or maybe it wasn't the first one of the first ones. I got free tickets to go see Bruce Springsteen. And I went with my ex at the time, and after about 20 minutes, we decided to leave the concert because it was the worst sounding concert ever. And in the process of leaving, we moved about 1,000 feet walking towards the exit, and the sound was completely different. It was like night and day. We were sitting in some region of the stadium where the speakers were interfering in just such a way that the sound was all garbled, and then just moving another 1,000 feet away was like night and day in terms of the sound. It was kind of interesting. Okay, going back to this. Sound, F5, sorry. Okay, so one other thing. This is why if you sing in the shower, you feel like you sound really, really good. And when in reality, you don't. Even I think I sound good in the shower. And the reason is most showers are covered with tile or something which is very rigid, very smooth. And so the material that showers are made of reflects sound really, really well. And so what you end up having, as if you had a speaker here, you're going to hear some sound coming straight from the speaker to you. But you're also going to hear sound that reflects off the different surfaces. Well, one, if you have too many reflections, that can be bad. We call that reverberations. But ignoring that, our voices tend to sound deeper, or maybe not deeper, but more full in a shower, because we're not only hearing sound coming straight from, the speaker or us, but it's reflecting off the tile and things like that multiple times. So we're getting sound from multiple sources. Okay, quick little question. Why is an echo weaker than the original sound? And I don't want to spend a whole lot of time. The answer is, anytime sound hits a surface, some of it's going to get reflected, some of it's going to get absorbed. So two different reasons. Sound gets weaker with distance, right? So a echo has to travel a certain distance, reflect, and then come that distance back. Farther sound has to travel, the weaker the sound gets. But the other reason is, anytime the sound hits a surface, not all of it's going to get reflected. Some of it's going to get absorbed. If some of the sound gets absorbed, the sound's not going to be as loud as it was before. Okay. Let's just quickly talk about interference, and then I want to talk about just two last things. So waves can interfere. We talked about that in chapter 19. If I have two waves that are at the same place at the same time and are identical, then these two waves interfere in such a way that they produce a wave that has a bigger amplitude. We call that constructive interference. Well, you can also have destructive interference where the two waves are, in a sense, like mirror images of each other. So like this wave, when this wave here is peaking, this wave here is at a minimum. When this wave here is at a minimum, this wave is peaking. When I add these two together, I basically get destructive interference. And if we're talking about sound, destructive interference results in no sound at all. So had we been on campus, what I would have done is I would have played from the two speakers in the front of the classroom a pure note. And what I would have had is people walk around the classroom, and you would find certain regions of the classroom where you have destructive interference happening and there's hardly any sound at all. And then you move a little bit farther and you'd find a region of the room where there was constructive interference and you hear a much louder sound. There's no way to reproduce that on the internet. Okay. So if you're a musician, I don't know if you know this, but because most people now just use fancy little electronic things to tune their instruments. But way back when, the way you used to tune instruments is with tuning forks. And a tuning fork is basically just something that's designed to move back and forth at the exact same frequency every time you hit it. So I have tuning forks on campus that have all different frequencies. Every time you hit it, it oscillates back and forth at that exact same frequency. All right, so let me discard. I want to show you what beats are, and there's no way to easily show this, so I want to just give you a quick little animation showing beats. All right, am I still sharing this? Yes, okay. So let me just play this. So pause for a second. So that tuning fork he hit, or whoever, 250 hertz tuning fork, which means it oscillates back and forth 250 times a second. That is the frequency of the sound wave it produces. So this one is 238 hertz. So it oscillates back and forth 238 times a second. That wah, 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 wah. Those are called beats. And the very simple thing for beats is, let me just show you actually on PowerPoint. New stop share, share screen, PowerPoint. Sorry about fast forwarding through all these. Okay, so if I had two sounds that were very close in frequency, in this case, we're talking about two tuning forks. One of them has a frequency of 440 hertz. The other one has a frequency of 438 hertz. If I sound those two tuning forks together, I'm not going to hear a 440 hertz sound. I'm not going to hear a 438. I'm going to hear these beats. This wah, 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 wah. And the frequency of the beats, very simple equation, is the frequency of the beats is just equal to the difference between the two frequencies. Difference between the two frequencies. So for example, if this is 440 and this is 438, my frequency of the beats would be 440 minus 438. it would just be 2 hertz. So what I would hear, and a beat is this wong, wong. So here, if I had like instead of 440 and 238, 10 hertz and 12 hertz, and I sounded them together, what I would hear is a beat frequency of 2 hertz. So I'd hear wah, 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 and I'd hear 2 of those wahs every second. So this particular one, stop share. I don't know what the exact oh, so this would have been 12 hertz frequency. Let's do this again. So that wah, 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 wah. So I mentioned this, how did then people tune instruments before we had our fancy dancy electronic things? Let's say I had a string that was supposed to be a 440 hertz frequency. Well, if I want to know if it really is, what I would do is I'd pluck the string and I'd hit a tuning fork that had the frequency I was trying to match. If I hear beats, then I know the two frequencies are not the same. What I would do is I would adjust the guitar string, hit the tuning fork again, and wait until I don't hear any more beats. When I don't hear beats, then I know the 2 frequencies are exactly the same. Okay. Last thing I want to talk about is resonance. So actually, before I do, we just pause. What do we do? 9:30 to 10:15, and then office hours for a half hour. So I'm probably going to go for about another 15 minutes, and then we're going to be done chapter 20. Before I go into the last thing, resonance, I want to open it up and see if there's any questions I can answer.
I do have a question, not exactly on the lecture, but for in terms, because your email said that we have a celebration on Saturday. Are you going to talk about that towards the end, or?
I might touch on that, but I was going to talk about that next week. Just so you know, chapter 19 and 20 homework is due Friday, tomorrow, and then a quiz on Saturday on both chapters combined. And then next week, I'm going to talk about chapter 26 on Tuesday, finish chapter 26 on Thursday, talk a little bit about the celebration, but pretty much it's just going to be a much longer quiz.
Oh, I thought it was this Saturday. That's why I was asking.
Oh, no. This Saturday is chapter 19 and 20, quiz on chapter 19 and 20.
So you said it's going to be together. Is it going to be like just like still 10 questions? Or
It'll
is
be
it going to
10
be 20?
questions, 5 from chapter 19, 5 from chapter 20.
Okay, for sure.
So there's a separate homework for chapter 19, a separate homework for chapter 20, but the quiz is combined. Okay, quick little demonstration first. What do I have that I can drop? I've got a pen and a, not really. Okay, little demonstration. I've got actually an 1898 Susan B. Anthony dollar. Woo, you cannot see it. And I've got a pen. I'm going to drop either one or the other off to the side. See if you can figure out which one I dropped. Which one was it? Obviously, it was the coin. So here's a question. Every time I drop this coin, it's basically making the same sound. Maybe a tiny bit different, but if I drop a pen, it's always making the same sound. Why is that? All sound is produced by something which oscillates back and forth. The frequency that it oscillates back and forth at is the same as the frequency the sound wave is. So whatever frequency it's oscillating at is the frequency of the sound wave we'll hear. So if every time I drop a pen, it makes the same sound, that's because every time I drop it, it's oscillating back and forth at the same frequency and producing the same frequency sound wave. Well, let's continue with this. Come on. So all objects sort of have a characteristic sound because all objects basically have what's called a natural frequency. So like a tuning fork, every time I hit a tuning fork, it oscillates back and forth at the exact same frequency because that's the natural frequency of the tuning fork. Everything that can oscillate back and forth has a natural frequency. A glass has a natural frequency. Keys, if I drop them, have a natural frequency. Or let's say I push a child on a swing. The swing itself, if I just let it go, has a natural frequency that it's going to swing back and forth at. Question is, could I make an object oscillate at a different frequency than its natural frequency? For example, if I pull a swing back and let it go, it's going to oscillate back and forth at some frequency. We didn't cover that in this class, but it only depends upon a couple things. One of them is the length of the swing. The other one is the acceleration due to gravity. Could I cause a swing to oscillate at a different frequency than its natural frequency? And the answer is yes. If I exert a force and I push the swing at a given frequency, I can cause it to oscillate at a different frequency than it normally does. We call this forced vibrations. This is me forcing an object to vibrate at a specific frequency by applying a force to it. Here's the thing. Well, let's imagine, the swing going back and forth. If I'm not paying attention and I'm just like randomly pushing, sometimes I might be causing the swing to go higher if I time my push just right. Or I could be causing the swing to start to swing less and less and less if I don't time my pushes right. Well, if I time my pushes so that the frequency of my pushes matches the same frequency that the swing naturally wants to go back and forth at, I can cause this swing to go higher and higher and higher. Basically, I'm increasing its amplitude. And this is what resonance is. Resonance is a dramatic increase in amplitude that happens when the frequency of forced vibrations matches an object's natural frequency. So again, I wish I had a pendulum or something, but a mass in a spring, if I pull it down, will oscillate at a given frequency. A pendulum, if I pull it and let it go, will oscillate at a given frequency. Well, if I exert a force on those systems at just the right frequency, the same frequency it wants to oscillate at, I can cause this to have a huge increase in amplitude, and that's what resonance is. So if you've ever seen a picture of somebody breaking a wine glass, so let me open this up. Woo, Jesus, excuse me. Why can't I, let's.
In 1940.
Oh man, none of these are opening. Okay. Let me stop this for a second. See if I can share a video. Resonance. Wine glass.
All
right. What I was going to show you is an old commercial from Ella Fitzgerald from Memorex. So a little history lesson. Way back before MP3s and CDs, there were these things called cassette tapes, and Memorex was sort of the brand. And their whole tagline was, is it real or is it Memorex? And what they had was let me see if I can do this one more time. Wine glass. Let's open it with Windows Media Player. Will that work?
Believe it.
No. All right, anyway. What it was showing was her breaking wine glass with her voice, and then they recorded it, and they played the recording back, and it would also break a glass. But the thing about the commercial is the wine glass that she broke with her voice was a different glass than they used with the recording, which I was going to show you indicates that it wasn't a perfect recording. But let me show you what happens when a wine glass. Come on, why are you not opening? Okay, so can I share this one with you? Share screen. Whoops. All right, so 1 second, experiencing technical difficulties. Stop share, share again. Do that one more time. So if you've ever seen or heard or saw the demonstration of a wine glass being broken by a singer, wine glasses also have a natural frequency that if I were to like pluck this glass, that it would naturally oscillate at. Well, if I were to push the glass at that exact same frequency, then I could cause the amplitude of the oscillations to increase more and more and more. Well, that's what's happening when a singer breaks a wine glass, is if they can sing at the exact same frequency the wine glass has, then it's like pushing a child on a swing at just the right time. It causes the amplitude to increase dramatically until basically it can oscillate enough that it'll break. Let me show you. I got a few different examples of resonance here I want to show you. Let's do Tacoma Narrows. So I don't know if you've heard of the Tacoma Narrows Bridge, but there was a bridge in Washington where the wind was hitting it at just the right frequency to cause this bridge to start to oscillate wildly. So this, oops, come on, you. Stop share for a second. Sorry, I don't know why it's doing this. Start share again. Nope. Technical difficulty. Okay, so this is the result of wind hitting a bridge at just the right frequency and causing the bridge to start to oscillate at bigger and bigger and bigger amplitudes. Eventually, this bridge collapsed, and I'll show you a video of it. But this was just from resonance. Even bridges, anything that can sort of oscillate, everything has a natural frequency. And if I apply a force to it at that exact same frequency, I can cause what's called resonance and cause this object to increase in how much it is oscillating. Here's another just interesting video, just a couple more and then we'll be done. So this is, I found this on military.com, believe it or not. This is a resonance test for a helicopter. So going back, this entire helicopter blade structure has a natural frequency that it would tend to oscillate at. And at some point, as these blades are starting to slow down, they end up rotating at just the same natural frequency that this thing has, and it causes it to move back and forth at bigger and bigger amplitudes until this. Really good thing that they, do this test, because you can imagine if you're in this helicopter landing, that's not good news. All right, I want to show you one more video. I renamed this video Mystery, just so you couldn't tell what it is right off the bat. I'm going to show it to you and see if you can figure out what it is. I'm going to give you the hint that this has to do with resonance. So let me share this again. Share screen. All right, this is a resonance phenomenon. See if you can figure out what it is. It's not a fortune cookie. One more time. All right, anybody have any guesses as to what that is? I'll give you a hint. It's a medical procedure. Any guesses, any guesses? And the answer is?
An MRI.
Ah, close.
Damn it.
Shattering a kidney stone. So let me just play that one more time and I kind of explain it. So everything has a natural frequency, even kidney stones. And what they're doing, you can't see it or hear it, they're hitting it with very high frequency sound waves. And they're hitting it with the exact same frequency sound wave that matches the natural frequency, causes it to oscillate back and forth. and eventually shatter, and then it's much easier to pass the kidney stone if it's broken up into lots of little pieces. Okay, so let me just quickly summarize resonance, and then we are done with chapter 20. So resonance is when you are exerting the force on an object at the frequency that matches the object's natural frequency. When that happens, it causes the amplitude of that oscillating object to increase dramatically. So a few examples of this. So one, pushing a child on a swing. Where's my, no, that turn off. What's happening here? Draw. Okay, pushing, what's happening? I just lost my Bluetooth connection. Okay, so pushing a child, oh, there we go. Pushing a child on a swing. So, you know, if I'm not looking and my daughter's like, Daddy, push me higher, and I'm just like, yeah, whatever. And I just push every so often. Sometimes I'm going to be helping her out and pushing her higher, sometimes not. But if I time my pushes just right so that they match the frequency the swing wants to naturally swing at, then I can increase the amplitude of the swing. Singer breaking a wine glass, right? If the singer's voice can sing at the frequency that exactly matches the natural frequency of the glass, we can get that to explode. I didn't go into this, but whenever you're tuning a radio, believe it or not, electric circuits also have what's called a resonant frequency. And what you're doing when you're tuning a radio is you're matching the natural frequency of the circuitry inside the radio to match the frequency of the radio wave that you're trying to pick out. So, you know, you can probably tune into what, 50 different stations? That means there's 50 different radio waves at the location of your antenna hitting it at the same time. What you're doing when you're tuning a radio station is you're preferentially picking out one of those radio stations, just a specific frequency, by matching the frequency of the circuitry in the radio. Troops breaking step across a bridge. So there's actually a really cool Mythbusters video about this. So I don't know if this is true, but the story is in the 1800s, you had a troop of soldiers that were marching across the bridge, and they're all marching in step. And they're all marching at some certain frequency. The story goes that whatever frequency they were hitting at, matched the frequency of the bridge. And in the process of all of these soldiers marching across the bridge, they caused the bridge to start to swing and collapse. It's not clear whether that's a true story or not, but because of that, they say is whenever troops are marching across a bridge, they don't have them march in unison, they just have them breaking step. A couple other things. This is one was for me. I had a car where every time I hit, I think it was like 58 miles an hour, I would hear this annoying rattle inside the car. The reason is there was a loose nut somewhere in the car. And again, anything that can oscillate will have a natural frequency determined by certain characteristics that it'll oscillate at. Well, at 58 miles an hour, whatever speed it was, my car would tend to shake at the exact right frequency to cause this nut to shake wildly, and it was just this really annoying sound. I already kind of showed you the Tacoma Narrows bridge collapse, breaking a kidney stone. Here's another one. Have you ever gone to a concert where there was really, really loud music playing, especially bass, and you had this pleasant buzzing feeling inside your body? Irregardless of anything you might have done before you went to the show, it ends up internal organs also have a natural frequency, and it tends to correspond to bass, which is a low frequency. So if you're near a speaker that's playing loud bass music and it feels like your stomach, your internal organs are vibrating, they are. That sound can actually cause your internal organs to start to oscillate back and forth, just like a sound wave hitting a glass and causing it to start to oscillate back and forth. And I won't touch, well, I'll just touch on, I call this the Calvin and Hobbes bathtub tidal wave. And I don't have a video to show you, but You ever taken a bath and you sort of move forward and it sends this little wave of water that can then reflect and come back? I don't know if you've done this, maybe it's just me, but if you sort of keep moving back and forth and you time just right, you can get these waves to start getting bigger and bigger and bigger, and eventually you get this bathtub tidal wave. Okay, so refraction of sound, we're not going to cover. So let me pause. So I went, where are we going to? 10:45. So I got about 10 minutes sort of that I'm going to do office hours section. I'm done chapter 19 and 20. What I want to do is, if there's no particular questions, sort of end the lecture portion, start the office hours portion. And what I'm going to do is, if there's no office hour questions, I'm just going to start going through the chapter 19 and 20 homework, answer some of the more challenging questions. So stick around for a minute just in terms of the lecture portion. If there's any questions about what I just covered for chapter 20, I'll answer those. If not, sort of just do office hours portion and then answer homework questions if there's no questions from people. Thank you, everybody who joined in. Pause for a minute. Questions, throw up a hand, unmute yourself. Let me know if you have any questions from chapter 20. And again, just keep in mind chapter 19 and 20 homework due tomorrow by midnight, 11:59. Saturday, quiz on chapter 19 and 20. Thank you, everybody. If you don't want to stick around for office hours, then we are sort of done with the lecture portion. If you want to stick around, I'm going to kind of go through a few of the homework problems from chapter 19 and 20, answer any questions people have on those. All right, so what is that? Am I over here? Why is this? Oh, I have an auto shut off. That's why this thing keeps. Okay, so I'm going to then share the screen. Thank you, everybody, and go through some homework questions. And if anybody has a question as I'm going through this, let me know. Got about what, 8 minutes. Okay. So let me just answer a couple of these that might be a little bit more challenging or confusing. Let's turn this on. Is this working? Okay. So let me look at number 4. This is from chapter 19. It says, how many nodes, not including the endpoints, are there in a standing wave that is 2 wavelengths long, 3 wavelengths long? So for a standing wave, remember that's a wave that appears not to be moving. A wavelength for a standing wave is basically 2 of these segments that are sort of oscillating back and forth, looking like they're not moving anywhere. So this right here, this would be a standing wave that is 1 wavelength long. So in this case, if I want to know something about standing wave that's 2 wavelengths long, here's 1 wavelength, here's the second wavelength. So my standing wave would look something like this. Now, generally the endpoints are considered nodes. Well, they are, but this says not including the endpoints. So if I was to include the endpoints, a node is where I have no amplitude. Basically, it's where the string is not moving at all. So the nodes here are, I got 1, come on. I've got 1, 2, 3, 4, 5 nodes. That's how many nodes there would be if I was including the endpoints. But in this case, they said not including the endpoints, so the answer would be 3. I've got 1 here, 1 here, 1 here. And then how about for 3 wavelengths long? I'm going to let you think about that one. A couple other ones to go through. This one was kind of a challenging one. Astronomers find that light emitted by a particular element at one edge of the sun has a slightly higher frequency than light from the element at the opposite edge. What do these 2 measurements tell us about the sun's motion? So this one's kind of challenging, but we have good enough telescopes where we can look at the light emitted from, well, a close star, but not the star as a whole, but just certain sections of it. So let's say I were to look at 2 different sections of the sun. Well, our sun is rotating. And so if you imagine our sun rotating, I don't know how best to draw this, but let's say it's rotating sort of in this direction. Then this piece right here is coming towards me. You know, if I imagine the sun rotating, at one point, part of it's coming towards me, and then this point might be going away from me. Well, here's what's really cool. Because of the Doppler effect, if a source of waves is moving towards you, you're going to detect a higher frequency. If a source of waves is moving away from you, you're going to detect a lower frequency. So if I look at the sun, and I can look at different edges of the sun, as the sun, can I do this? As the sun rotates, you know, this part is moving towards you, this part is moving away from you. And so if I were to look at the light from different parts of the sun, the part that's moving towards me is I'm going to detect a higher frequency. The part that's moving away from me, I'm going to detect a lower frequency. So what does this tell us? It tells us that the sun is rotating. And by looking at how much different the frequency is on one side versus the other, we can actually figure out the rate at which the sun is rotating. Very cool kind of astronomy. All right, a couple more I'll answer. Let's look at chapter 20. This one's kind of a cool one. In Olympic competition, a microphone detects the sound of a starter's gun and sends it electrically to speakers at every runner's block. Why? Well, in Olympics, the difference between a gold medal and a bronze medal or a silver medal is often 1/100 of a second or less. So imagine I've got, you know, here's the starter gun, and I've got these 4 different racers. The speed of sound isn't infinite, right? Sound travels at about 750 miles an hour. So if everybody's waiting until they hear the sound from this gun, well, this person who's closer is going to hear the sound before this person who's farther away. And even though it may only be 1/100 of a second difference or even less, in the Olympics, where every split second counts, they need to take that into account. So instead, what they do is they have these little speakers next to everybody's starting block. And what happens is they record the sound from this starting gun, and they basically send it to all these speakers that are at each starting block. And the speed of light is pretty much, well, it's not infinite, but the speed of light is unbelievably fast. The signal in a wire basically travels at about the speed of light. And so all of these runners are now going to hear the sound at the exact same time. Whereas if I just had to rely on sound traveling through the air, the people farther away from the starting gun would be at a disadvantage. What other ones? So let me just touch on this last one about beats, and then I think we will call that good. Suppose a piano tuner hears 3 beats per second when listening to the combined sound from his tuning fork and the piano note being tuned. After slightly tightening the string, 5 beats per second are heard. Should the string be loosened or tightened? So one, the beats, the frequency of the beats that you hear is always basically equal to the difference between the 2 frequencies. Difference between the frequencies. So if in the process of tightening or loosening a string, I hear more beats per second, that means I'm getting farther away from the frequency I'm trying to tune, which means I want to be doing the opposite. So here, if I tighten the string and now I hear 5 beats per second instead of 3, then I'm getting farther off. I don't want to tighten it more. What I want to do is loosen it. So in this case, I would loosen the string so I'm not hearing as many beats per second. And ideally, what I want is no beats. When I hear no beats between the tuning fork and the plucked string, that means those 2 frequencies are exactly the same. All right. Allison, Angelique, Laura, any questions I can answer before we tune out for the day? Going once. Going twice.
Thank you.
Thank you, Laura. Thank you, everybody. Have a wonderful weekend. Don't forget homework tomorrow, quiz on Saturday. And yeah, hopefully I'll see you guys on Tuesday.
Have a good day.
You too. Have a great weekend.